Quantum cryptography is assumed to be almost absolutely safe, if performed properly. The reason lays in the funny properties of the quantum reality, which allows the detection of any eavesdropping on quantum encrypted, meaning entangled, data streams. But what if this basic assumption is fundamentally flawed? After all, the current quantum theory, on which the whole quantum cryptography is based, does not contain gravity and thus cannot be considered complete. So, what if a completed theory, a quantum gravity, does destroy the illusion of an absolutely safe cryptography by the means of quantum entanglement? What if a whole world became dependent on this quantum encryption technology simply because quantum computers, or even worse, quantum gravity computers, can crack each and every code within a blink of an eye, thereby destroying the safety of all classical, non-quantum and non-entangled cryptographic means, and suddenly there was a way to read all quantum encrypted messages without the slightest risk of detection of the eavesdropping? What if only one entity possesses such a technique and nobody else does know about this, or even isn't aware of its potential existence? In the presentation, it will be shown that quantum cryptography is just another Enigma illusion. Quantum gravity will make sure of that. But the latter also guarantees the existence of an ultimate solution to each and every cryptographic problem. A theory of everything for which we are aiming here should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In previous presentations in this series, we have already shown how we can extract the Klein-Gordon equation from the Einstein theory of general relativity, see Part 2, and that matter does not need to be postulated, see Part 1. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who had derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation now, we will show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. As we have already shown in Part 1 of this series that we do not need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of space-time, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation now yields a much more complex kernel. Treating it like the classical Einstein-Hilbert action and demanding the whole integral to vanish gives us the quantum Einstein field equations. Thereby, the red ellipse shows us that the classical Einstein field equations are a part of the new set, making out the metric or G-related terms, while the rest is connected with a scaling function and thus the local volume of the spacetime under consideration. Taking the full kernel of our scaled Einstein-Hilbert action and assuming the gravity part to be small against the volume, we end up with a scalar differential equation. It already was shown in our earlier presentations that this equation simplifies to the standard quantum equations when we assume certain metrics. The characteristics of such metrics coincides with the typical and often used metrics like the Minkowski metric in Cartesian, spherical or cylindrical coordinates. Here now, however, we leave the metric general. incorporation of the functional wrapper capital F of F property, we obtain a partial differential equation on F. Please note that the integrational kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. We already treated this path in our second part of the series, where we derived the metric, which is to say the generally quantum relativistic Klein-Gordon equation. Here, however, where we insist on completely general metrics in an arbitrary number of dimensions, our result is a bit more complicated. In fact, it contains all quantum equations of non-Dirac type, whereby regarding the latter, we refer to our presentations part 3 and 12 of this video series. Please note that this equation in fact simplifies to the Klein-Gordon equation in the case of special metrics. We note that with the approach used here, we should discuss the following issues. The direct application of the Einstein-Hilbert action does not give us the perfect Laplace operator for all metrics. See therefore the previous slide. And there is no separate equation, which is to say the equation we have for capital F of F, even though already clearly mirroring the classical quantum equations, is only a part of the classical Einstein field equations. We try to solve the problem via an additional variation. This time, the variation is with respect to the function f, and we apply the so-called functional derivative, for which we refer to the standard textbooks in theoretical physics. Here on this slide, we assumed to have performed the f variation after the standard Hilbert variation under the assumption of weak gravity. And we see, the red ellipse, this time we obtain a perfect Laplace operator. It should explicitly be pointed out that we can obtain the same result when applying the f nudging, which is to say the functional derivation of the Einstein-Hilbert action, before the usual Hilbert variation with respect to the metric tensor. Again, we obtain the perfect Laplace operator. Introduction of a suitable condition for the wrapper function capital F gives us the quantum gravity Klein-Gordon equation. Now we see, when building a quantum cryptographic communication on the 100% perfect metric mirroring our practical setup, and applying solutions to the complete scalar equation as shown in the middle of slide 12, we could in fact assume the metric or tensor part of the variation to vanish, and thus use our simplification step from slide 9 of this presentation. Then we end up with a purely scalar equation, it can be seen in the middle of the previous slide, and could assume a quite secure way of communication. The other possibility is to know and control the whole variation, including its tensorial part, and then quantum gravity secure, meaning check, the communication via the quantum Einstein field equations as given in this presentation on slide 8. Alternatively, we may also just start with a variation concept with respect to the function f. However, following Heisenberg's causal chain and assuming that every trial to determine the volume of the spacetime at a certain position in this very spacetime automatically changes its metric tensor and, vice versa, automatically leads us to a quantum gravity uncertainty principle, which also automatically compromises our cryptographic securing process. The winner of this game, so there will ever be one, obviously will be the one whose technology allows measurement as close as possible to the quantum gravimetric limit of this most fundamental uncertainty. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because A. At the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and B. His main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. Well, these new insights now open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in our talks. Next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via working quantum gravity computer tech. Everything else are service projects.